Hello everyone, myself Muskan Patel from 6M Chanakya. My topic of today's representation is Introduction to Matrix Representation and Homogeneous Coordinates. In the field of computer graphics and 3D modeling, matrix representation and homogeneous coordinates are fundamental concepts that enables the manipulation and translation of the object in the digital space. These mathematical tools provides a powerful flexibility to perform complex operations like scaling, rotating, and translating objects with ease. Now, motivation for using matrix representation. Matrix representation offers a powerful and versatile way to work in 2D and 3D graphics and animation. They provide a unified framework for transmission points, vectors, and objects using a common set of operations. Matrix allows for easy composition and concentration of multiple transformation, enabling complex visual effects and scenes manipulation. Homogeneous coordinates, in particular, extend the utility of matrix by allowing for the representation of translation, rotation, and scaling. Transformation is a consistent manner in unified approach, simplifies mathematical computation, and enables seamless integration of different type of transformation within a single framework. Now let's see the representing points and vectors in a homogeneous coordinates. Homogeneous coordinates. The homogeneous coordinates is a way of representing points and vectors in a higher dimensional space. In 2D, a point x, y is represented as a 3D vector x, y, 1, where the third component is called the homogeneous coordinate. And let's see the advantages of homogeneous coordinates. The main advantages of using homogeneous coordinates is that it allows for unified representation of various geometrical transformation such as translation, rotation, and scaling using matrix operation. And the transformation in homogeneous coordinates are representing transformation. In homogeneous coordinates, transformation like translation, rotation, and scaling can be represented as a 4 into 4 matrix. This matrix operates in 4D homogeneous coordinates vector to apply the desired transformation, allowing for unified mathematical representation of various statistical operations. Translation. Translating a point in homogeneous coordinates is achieved by adding the translation vector to the first three coordinates of the 4D vectors. The translation matrix encounters this operation, allowing translation to be easily combined with the other translations. Rotating and scaling. Rotating and scaling are represented by 3 into 3 submatrix within the 4 into 4 homogeneous translation matrix. These submatrix apply the desired translation and the scaling to the first three components of the 4D vectors, while the fourth component ensures the translation is correctly applied. The translation, rotation, and the scaling using matrix. Translation. Translation, an object using a matrix involves adding a constant offsets to the coordinates of the object. This allows you to move the object to a new position without changing the orientation or its size. Rotation. Rotating an object using a matrix involves applying a rotation transformation to the coordinates. This allows you to spin the object around a specified axis, like the origin or the custom consume pivot point. Scaling. Scaling an object using matrix involves multiplying the coordinates by a scaling factor. This allows you to resize the object, make it larger or smaller while revising its properties. Projection and perspective transformation. Perspective projection. Perspective projection is a fundamental technique in computer graphics and 3D modeling. It stimulates how the human eye perceives depth and distance, creating realistic three-dimensional illusion on a two-dimensional surface. This type of projection is essential for creating accurate depiction of object, scenes, and environment. Orthographic projection. In contrast to perspective projection, orthographic projection maintains parallel lines and perceives the true size and shape of the object without the distortion caused by perspective. This type of projection is commonly used in the technical drawing, engineering, schematics, and architectural plans where accurate measurements and the properties are crucial. Camera view frustum. The camera view frustum is a key concept in 3D graphics and animation. It represents the region of space that is visible to the camera, defining by the camera's field of view, near and far clipping planes. Understanding the view frustum is essential for efficient rendering, visibility, and creating realistic camera movements in 3D environment. The advantages of homogeneous coordinates, unified transformation, projective graph geometry, numerical stability. Unified transformation. Homogeneous coordinates allows for unified representation of transformation like translation, rotation, and scaling using a single matrix. This simplifies the mathematical and make it easier to combine multiple transformations. Projective geometry. The homogeneous coordinates are essential for representing and manipulating projective geometry, which is crucial in computer graphics and computer vision for modeling perspective and performing tasks like camera calibration and 3D reconstruction. Numerical stability. Homogeneous coordinates can provide improved numerical stability compared coordinates, particularly for transformation like perspective projection that precisely illusions near the camera planes. Limitation and consideration. While matrix representation and homogeneous coordinates often powerful tools for working in 3D graphics and transformation, there are some limitations and important consideration to keep in mind. Numerical precision can become a challenge, especially when dealing with large mathematical or complex transformation, which can lead to rounding error and other numerical instabilities. Additionally, the increased dimensionality of homogeneous coordinates can result in increased computation and complexity and memory usage, which can be concerned for real-time or research concerned application. Another key consideration in the handling of degenerate cases, such as where a point or a vector has a zero homogeneous coordinates. This case requires special care and can lead to division by zero and other numerical issues if not properly addressed. Developer must be mindful of the potential for unexpected behaviors when combining different types of translation such as perspective and offline transformation. Application of matrix representation and the homogeneous coordinates, computer graphics and animation, robotics and spatial reasoning, arguments and virtual reality, image processing and computer vision. Conclusion and the key takeaways. In conclusion, the use of matrix representation and the homogeneous coordinates has become a transformative development in the field of computer graphics and the 3D visualization. By the representing points and the vectors in a homogeneous coordinate system, we can elegantly perform complex transformations such as translation, rotation, and scaling using a simple matrix operation. This approach often numerous advantages includes the ability seamlessly integrates perspective projection and the handle points at infinite with ease. As we have explored the power of matrix representation and the homogeneous coordinates, unpointed many crucial applications for 3D modeling and image or to augment reality and the computer vision. The key takeaway for this discussion can be the importance of understanding the fundamental concepts of matrix representation and the homogeneous coordinates, as well as their practical application in the modern digital media and the technology. By mastering these techniques, developers and designers can be unlock the full potential of 3D graphics, creates a more impressive and realistic experience, and push the boundaries of digital real. As we continue to innovate and advance, the principle remains a cornerstone of the field, guides the future breakthrough and visual computing. Thank you for watching my video.